Everyone, this is Professor Monty. Today we're doing sections 1.3 and 1.4, so let's just jump right into it. 1.3 rather, as you see, is average rates of change. So let's kind of sketch something out here. Say we've got a function, and let's say this is hours, so this is time, and this will be miles. And say we're going someplace, and let's just say we've got a curve and it starts here and we start to go up here, and we've got some sort of curve like this. And let's say after 1 hour we're here, and maybe that's 50 miles. And then after 3 hours, we're up here. Let's see, let's extend this up a little bit. And at 3 hours, maybe we're here, and say that's 90 miles. Okay. So what we're talking about here is average rates of change. So at any point along there, we see that we don't have a linear function, which means we're changing at different rates. And in fact, the rate that we're changing, say here at 50 miles, is we're going up pretty steep, but at 90, we're not going up very steep at all. We're about like this. Well, what we can do is we can look at those 2 points individually. This point will be at 1 hour, we're at 50 miles, and this at 3 hours, we're at 90 miles. And if I want to find my average rate of change, let's think about how we would do that. So my average rate of change is going to be, now I'm going to use the triangle for change. I stole that from physics. It's going to be the change in my miles over the change in my time. Well, my miles, I went up to 90, but that coming from 50. So the difference in my miles is going to be 40 miles. The difference in my time, I went up to 3 hours, but I started at 1 hour, so that was 2 hours worth of time. Well, notice if I reduce this, I get 20. And what that actually is, it's 20 miles per hour. That's my rate. And does it mean that I went 20 miles per hour that whole time between hours 1 and 3? No, it doesn't mean that at all. But that was my average time. Remember, at hour 1, I was going up at a faster rate. I was increasing faster. My miles were increasing faster, but then my miles weren't increasing very fast as I got close to 3 hours. But that was the average rate of change. Notice what that is. If I draw a line through here, through these 2 points, now we call that a secant line. And a secant line just goes through 2 points on the curve. But what's happening is that secant line, what I really found miles over time, does that look familiar to you? That was the change in y over the change in x. Well, we're saying that's my average rate of change. Average rate of change. But we've seen that before. Some of you already recognize that's just the slope. That was really y2 minus y1 over x2 minus x1. So the average rate of change just means the slope. Specifically, it's the slope of the secant line. Let's write of secant line right here. So the slope of the secant line is my average rate of change. It's not a new concept. We may not have talked to it or talked about it as the average rate of change, but that's all the slope is. If my function itself was just that black line, notice it's going up at the same rate all the time. We call that the slope. The slope is the rate of change. Well, for a line, it doesn't change, but for a curve, it's going up faster at some points and slower at some points, or down, depending on the shape of the curve. But if I take 2 points in there, the average rate of change is just the slope of that secant line. Okay, so that's where we start there. What we're going to look at is we're going to look at average rates of change from what we had called before the difference quotient. So let's scoot this up a little bit. If you remember the difference quotient that we saw in algebra, the difference quotient, what it looked like, it's f of x plus h minus f of x all over h, whatever in the heck that all means. Well, what that really means, it's the slope of that secant line. Now here's why. Here's what's happening here. So let's say I have a curve, and let's say the curve looks like this. And I'll take a couple points on this curve. Maybe one's here and one's here. Again, I can draw a line through there. Let's make this line blue. There's the secant line through those 2 points. Well, we know the slope of that's the average rate of change. But here's what they do. Here's where this new formula comes from. I can call this x1 and I can call this x2. Well, if this black curve is my f function, we'll say y equals f of x. Sometimes you just put an f up there. Well, the point straight across here, this would be f of x1, right? It's the function value when at x1. This point straight across from here is f of x2. And so in fact, if I go back up here, I can write that as my change in y, f of x2 minus f of x1. Oops, that didn't come out as nicely as I'd hoped. Let's see, let's erase that. Okay. So it's f of x2 minus f of x1 over x2 minus x1. That's just that's a function way of drawing the y values. Remember, the y values are always the function values. But that's what I have here. The slope, that's the slope of this. But here's what they say. They say, let's take these 2 points here, and we're going to make that distance, we're going to call it h. So h is just that distance, x2 minus x1. We'll just put it there, but we see it in the picture. We know what it represents. Well, if I've got that, what I can do, let's put this in green. I can take this point and let's just call this first value x, because then this is going to be the point x comma f of x. This point, I just want to leave it in terms of x. I don't want 2 different x values. So I'm going to call it, I start at x, but then I add h to it. So this point is the same x, but it's h away from it. So it's just x plus h, which would make this point up here, x plus h, comma, f of x plus h. The advantage of doing that is now I only have one x value. I have this h that moves x to another x value, but they're still just based on x. I don't have x1 and x2. I just have x and then x moved over. The reason that's important is because now if I look at the slope of that, so let's look at the slope. Again, that's y2 minus y1 over x2 minus x1, same as it always was in algebra. But the second y value is over here. It's that f of x plus h. Minus the first y value, f of x, all over, well, the second x value is x plus h, minus, and the first x value is just x. But notice this x minus this x cancel each other out. So what I get is the slope is f of x plus h minus f of x, that's the top. The bottom, these x's cancel out. So it's just h. And that is what we called the difference quotient before. But notice the difference quotient is still the slope of that secant line. It's the average rate of change. So it's just a different way of writing the average rate of change of the function. Let's just say of f of x. But it's the same idea. It's the slope specifically of this blue secant line in this case. Okay, so that's the idea there. So let's jump up on that a little bit. We're going to take that idea. We're going to do a couple problems. So let's look at the first problem I want to look is problem 14 out of the book. So I'll just write it down for you. Problem 14, they give us a function g of x, and they say that's just negative 3x squared. And then they tell us, semicolon, x1 is negative 2, x sub 2 is 0, I'll put a comma there. And what they're asking us is they say, find the average rate of change of, in this case, of capital G of x between x1 and x2. Well, the average rate, again, that's just the slope. The slope is the average rate of change. Well, so what's it going to be? It's going to be the change in the y values. So it's going to be g, whatever the function value is, at x2 minus g of x1. That's the change in the function over the change in x2 minus x1. The change in the y's, that's the top, over the change in the x's, that's the bottom. Well, if we go ahead and do this, that's g of, well, x2 was 0, minus g of x1 was negative 2, all over 0 minus negative 2. We'll put those in parentheses, so they're both in parentheses. Well, g of 0 means we go up to the function and we plug a 0 in right there. So g of 0 is just negative 3 times 0 squared minus negative 3 times negative 2 squared. So there's my first one minus my second one. All over, well, that's really 0 plus 2. Well, if I work these out, 0 squared is 0, times negative 3 is still 0. Minus negative 2 squared is 4. 4 times negative 3 is negative 12. So it's 0 minus negative 12. All over 2, which of course is just 12 over 2, which is 6. So that's the average rate of change. Now that's the average rate of change between negative 2 and 0. Let me draw you a picture to show you what we just found. So what we did, remember the graph g of x is negative 3x squared. Well, if you remember what that looks like, it's a parabola, goes through the origin, opens down, looks something like this. No, we'll just draw in black pen. It goes like this. The 3 makes it pretty steep, but it looks something along these lines. And what we're doing is we're going from negative 2 to 0. Well, let's get another colored pen here. At negative 2, when we plug that in, at 0, well, we can just go it this way. At negative 2, we had a y value. When we plugged in negative 2, we got negative 12. So we're at a point down here. That point is negative 2, negative 12. At 0, we got 0. So that's 0.00. And what we're doing is we're finding the slope of that line right there. That secant line that goes through there, this slope was equal to 6. It represents the average change in the function, or the average rate of change in the function between -2 and 0. But graphically, it's just the slope of that secant line. All right, so that's the idea. So they'll have you find some of these, and you just do it. We did this. Oh, it's g of the second point minus g of the first point, and then it's the second point minus the first point on the bottom. So it's the change in y over the change in x. Again, it's just the slope of that line. Okay, now what they want to do, let me show you a slide that we have in here. So let me pull this up and show you. We'll post it right there. I think that'll work. Let's take a look. It's this one. Guess I didn't need to pull that up all the way. So let's see. Let's copy that. And we'll go back here and paste this in. So what this is for some of the problems they've given us. It says for each function in exercise 21 through 36, A, find the simplified form of the difference quotient. Well, this is the difference quotient. We talked about that before. Notice it's the same difference quotient we developed. I don't want that there, so I'm going to erase it. So we'll erase that, but that's the difference quotient we're talking about. So find the simplified form of the difference quotient and then complete the following table. So they give us that table. So we use this for different problems. The first problem I want to do is problem 26. And what 26 gives us the function f of x equals x squared plus x. And what I need to do from that function, I want to find f of x plus h minus f of x all over h, right? The difference quotient, that's this. Well, f of x plus h means I plug in x plus h here and here. So that first piece is going to look like x plus h squared plus x plus h. That part is just the f of x plus h. And then minus f of x is just the function itself. It's the x squared plus x. So this part is just f of x. So there's my f of x plus h, all that, minus f of x, all over h. Now, what I need to do is I need to simplify that. So the first thing is, and this is where students kind of mess up sometimes, this x plus h squared, we need to do that correctly. So let me show it off to the side here. X plus h squared really means x plus h times x plus h. I can't distribute that squared across plus. I have to actually FOIL this out. So I'm going to say, oh, that's x squared plus xh plus another xh, order doesn't matter in multiplication, plus h squared. These are the same. So I add those together. I have one of them and another. I have two of them, 2xh plus h squared. That's just this piece up here, the f of the x plus h squared. That's all I did right there. Got a little too excited with my eraser. All right, so what I have, that first piece, x squared plus 2xh. Oh no, that's not a 2xh. Plus 2xh plus h squared, and then plus x plus h, minus x squared, distribute the negative, minus x, all over h. And then watch what happens. You know you're on the right track if this x squared cancels that x squared. This x cancels that x. And where you know you're on the right track, notice I have 1, 2, 3 terms left. If all 3 terms have an h in there, you're on the right track, because I can take those and factor out the h. So I factor out an h there, it leaves me with a 2x. Factor out an h there, I still have an h. Factor out an h there, it's just h divided by h is 1, but it's all divided by h. The reason I did that, because now I can cancel out the h's. And so my simplified form of the difference quotient is 2x plus h plus 1. That is my simplified. That came from here. That came from my f of x plus h minus f of x over h. That's my simplified difference quotient, what it represents. Because remember that f of x plus h minus f of x over h, that's the slope of the secant line, or the average rate of change. This is a formula, the 2x plus h plus 1 is a formula for the average rate of change, or the slope of the secant line. So this simplified here, I'm just going to replace that. So let's get rid of this arrow here, and we'll replace, and we'll say, oh, this is equal to 2x plus h plus 1. So now when I see, for instance, the 5 and the 2, I just plug the 5 in for the x and the 2 in for the h. So this first one is actually going to be 2 times 5 plus 2 for h plus 1. So I get 10 plus 2 plus 1 is 13. And then I do the same for the next one. It's 2 times 5, but this time plus h is just plus 1, and then plus 1 on the outside. So now it's 10, 11, 12. And then I do a similar thing. So what I'm going to get, 10 plus 0.1 plus 1. I get 11.1. And when I plug in the 0.01, 2 times 5 is 10, plus 0.01 is 10.01, plus 1 is 11.01. And if you think about what we did last time, so I've finished the problem. That's what they were looking for. That was find the simplified form of the difference quotient. So this was the answer here. That A. It's not a very good A, is it? Let's make it look a little more like an A so you know what you're looking at. That's the answer to part A. The table is the answer to part B. But let's think about what this means. Remember when we talked about limits last time, we are taking a limit as h. What's happening to h? Well, it started at 2, now it's 1, now it's 0.1, now it's 0.01. What I'm doing is I'm taking the limit as h approaches 0. And what I'm looking to see is if this difference quotient approaches some number. So formally, this is what I'm doing. I'm taking the limit as h goes to 0 of f of x plus h minus f of x all over h. If that equals some number, then that's going to mean something. And we're going to talk specifically about what that means in the next section. That's where we're going. So this is kind of leading us to do it. So they give us this and they have us do that with some of these. There's another problem that they have that's similar to this. I'm going to show you another one of these so we get another example. So this is problem 30. The function they give us, f of x, negative 2x plus 5. Again, they're asking us to do the same thing. So let me post that again, and we're going to fill this out. So this is for problem 30. So we're just new problem starting here. This is part of it. So for part A, we have to do the simplified form of the difference quotient. So for part A, we want f of x plus h minus f of x all over h. Well, in this problem, it's -2. We plug in the x plus h where the x was. So that is my f of x plus h. So it's the original function, just plug in x plus h where the x was. This minus f of x is just that whole function, -2x plus 5. So there's f of x all over h. This time I don't have to square anything, so this will be easier. I just distribute here. So I get -2x minus 2h plus 5. And then the minus, distribute the negative. If you want to think of it as a -1, that changes it to plus 2x minus 5 all over h. And again, everything's going to cancel that doesn't have an h. This time there's only one term left. So this had simplified actually to -2h over h. Oh, good heavens, I don't know what's going on there. Let's start that over. All right. This simplified to -2h over h. Of course, now we can cancel those h's. We couldn't cancel the h before because we had the terms, we had the pluses and minuses. We can only cancel the h if it's a factor, if it's being multiplied. That's why we had to factor it out in the previous problem. But I get as my answer here just -2. That's the answer to part A. The simplified difference, this whole thing is -2. Well, so part B is going to be kind of interesting or boring, depending on how you look at it to answer it, because when x is 5 and h is 2, there's no place to plug in the 5 or the 2 because there's no x or h left. They all canceled out. So this is just -2. And when we plug in 5 and 1, there's no place to plug them in, it's still -2. And 5 and 0.1, still -2. And 5 and still -2. Let me show you a picture of what that means. Because remember, the original function here, f of x or y, so y, remember that's what f of x means, is -2x plus 5. That's a line. If I were to graph this, I start up at 5, 1, 2, 3, 4, 5. I go down 2 and right 1, right? That's my slope. And I can draw my picture. So the graph, the function is this line right here. Any place on this curve, we're actually, let's erase this arrowhead here. We'll erase that whole thing. We'll go back here. If I draw this graph, and I go out to where x is 5. Notice if I plug in 5, I get -10 plus 5 is -5. So if I plug in 5, say there's 5, I'm down here at the point 5, comma, -5. That's my point on the graph. So when x is 5, I plug that into f of x, and I get y equals -5. So we can put a -5 right here. But what we're saying is if I look at the secant line between any 2 points, so when x is 5 and when x is 2 away from 5, so if I went over here to 7 and then came down, maybe the line's right here, well, this secant line has a slope of -2 because it's exactly the same line. If I go back and move the point instead of out 2 away, I only move it 1 away, say here, now I'm right here, it's the exact same line, has the exact same slope. So it doesn't matter how far these points are away from each other, the slope is still -2 because my function itself is just a line. Notice since my function is a line with a slope of -2 and the average rate of change means the slope, all of the answers are just the slope. So that's the slope of line but it's also the average rate of change. Doesn't differ from that. Again, because I have just a linear function. On the function before, I had an x squared, so it was a parabola. So it changes depending on how far the points are apart. Okay, so anyway, that was kind of an example of that. Let me show you an application in this section, then we'll go into the next section. So let's do this. Let's jump back. Let's move this up and out of the way. And I'm going to click here. That's where I'm going to paste this problem in. But let's go find the problem. And I don't think I can just grab it from there. I think I can just do this. Let's try. I see nothing that says, oh, there's copy. Okay, let's see if this works. So let's go back. Can I just lower that down? No. Not where I want to be. I want to be here. Let's try. Did that copy? Paste. It certainly did. Okay, so let's go ahead and do this. Total revenues, problem 52 from that section. Suppose Fast Trends determines that the revenue in dollars from the sale of X iPod holders is given by R of X is, and they give us that. And then they say, find and interpret the significance of the result to the company. So what they're doing here, notice this, R of 305 minus R of 300, that's just my change in R, revenue in this case, over my change in X, which is number of iPod holders. It's the slope. It's my average rate of change. Hopefully you recognize that right away when they said, hey, what in the world is this? Oh, it's the average rate of change. It says interpret the significance of the result of the company. So we'll interpret that when we're done, but that's all this is. It's a slope. It doesn't look exactly like the slope, but it's not far from it. It's, if we look up here, this part is my f of x plus h, or f of x2 minus f of x1, and there's x2 minus x1. So anyway, let's work that up. Let's erase this. I've just got too much stuff going on there. It looks a little too busy for me. But let's find. So we're going to do R of 305 minus R of 300 over 305 minus 300. All right, so let's look and see what's happening. So that R of 305, we go up to the function up here and we plug 305 wherever there's an X. So we get negative 0.001 times 305 squared plus 150 times 305. Okay, that whole thing is my R of 305. So we'll get that as a value minus, and we'll do the same thing with 300 to write it a little bit smaller because I'm running out of room, negative 0.001 times 300 squared plus 150 times 300. Oh, that fit fine. So that piece was my R of 300. Well, 305 minus 300, we'll just do that. That's 5. Well, let's see. I'm going to do this in my calculator, so I'm just going to plug in negative 0.001 times 305 squared plus 150 times 305. And I get, let's see, it's in dollars, so I'm going to go to the nearest penny. I get 45,656, and it's 0.975, so I'll say 98 cents. Minus, so that was my first one, minus, and I'll plug in the second one. All I have to do is change those 305s to 300s. And I get $44,910. It's all over 5. All right, so let's see. So we'll go minus Let me plug in that other number. And I get 746.98. All over 5. All right, let's talk about what's happening. This first piece here, let's do that in another color. This piece here was my R of 305. That means my total revenue for selling 305 of these iPod covers is $45,656.98. This value over here, my 5's kind of running into it, but this is my R of 300. That would be my total revenue if I just sold 300 cases. Well, that difference of $746.98, that's the difference in selling those extra 5 cases, going from 300 to 305. But I sold 5 more cases. So when I divide by 5, and I've got this in my calculator, so I'll just click divide by 5, I get, again, I have to round it off, but I get 149, and it's 0.396. We'll round it to 40. It's $149.40. Now remember, that top number represented the revenue. That's in dollars. That's why this is in dollars. Specifically, it's dollars. The bottom was 5 cases. They called them holders. What do they call them? iPod holders. So let's not call it a case. We'll call it a holder. So we made $746.98 to sell these 5 holders, or $149.40 per holder. Notice it's a rate of change. It's the change in dollars per holder. So it's the average. Did I sell them all for $149.40? Not necessarily, but that was the average of those 5. So what I would write, the significance is for increasing sales from 300 to 305 iPod holders, revenue increased by an average, right, because it's the average rate of change, of $149.40 per holder. I am very big on trying to make sure you understand what it is you find. If you find it's $149.40, yeah, you got the number right, but if you don't know what it means, who cares? So I always try to stress, what does it mean? Because if you know what it means, it's a lot easier to remember how to do it because it makes sense to you. Okay, so anyway, that's the end of that section. What we're going to do is we're going to jump into the next section, 1.4, and it's, to be honest, very theoretical, but it's the basis for using calculus for the rate of change. Okay. Here's my issue. Think about, consider, and I'm just going to draw a function. Y equals f of x. And let's draw a function, and we'll say the function looks something like this. Now, if I get a line, and I draw a line through here, and say it goes through these 2 points. That point that's going through 2 different points on there is going to tell us the average rate of change. Remember, that's a secant line. What I'm interested in this section isn't secant lines, it's tangent lines. Because where the secant line gives us an average rate of change. What I'm looking for is a tangent line. So say I'm at this point, a tangent line will just touch in that one spot right there. It kind of masks the curve. If you go along this and you think about a surfboard riding on a wave, any point that the surfboard's on the wave, that would be a tangent line. Notice right here, the tangent line's flat. Down here, the tangent line's going to look something like this. Over here, it's going to be flat again. Over here, it's going to be cruising like this. So these green ones are all tangent lines. Now, sometimes when we're looking at the tangent line is only touching the curve in that one spot. We have to be a little bit careful about that, because if I say I get a tangent line over here that would touch right there, well, it's going to come over here. It's going to touch the curve someplace else. If we're just looking where it's just touching the curve in the one point up here, then it's a tangent line there. But the whole line, if we're looking at the 2 points of intersection, it's a secant line between those two. So I'm going to erase that line because we don't want to look at that as a, oh, erase my secant line. I want to think of each of those green lines as a tangent line, because here's the problem. I can find the average rate of change of the secant line, but what if what I'm interested in is how is the function changing right there, just at that one point, not the average over these 2 points, but just at that one point. What I'm going to look for is I'm going to look for the slope of the green secant line right here. I'm looking for the slope of this line. So here's the idea. Slope of tangent line isn't the average rate of change of the function, is the instantaneous rate of change of the function. At a single point. And if we think about the example we used before, the beginning of the last section where we talked about how many miles we went over 2 hours, and we found, oh, on average, we went this speed, this many miles per hour. I don't want to know what I go on an average of 2 hours. I want to know right now what's my speed. In the car, it's easy. You just look down at your speedometer, and the speedometer says, okay, right now you're going this fast. I don't know how fast you're going on average, but I can tell you right now. That's what we're looking for, is right now. So the green line that I drew over here, I'm looking for how the function's changing right there at that point of tangency. And I know I can use the slope. I have a slope formula, but I have a huge problem with the slope formula here. If that green line, the tangent line, is only touching the curve in one point, I need 2 points to do the slope formula. It's y2 minus y1. I only have one y value, and I only have one x value. So here's what we do. We go back to that blue line, the secant line, and we find the slope of the secant line, because we know how to do that. That's the difference quotient. But then I say, well, really that in the green line, the big green line that I have there, those aren't the same slope. Well, there's a certain x distance between these 2 points, remember? We called that h. Well, let's have h be a little bit smaller. So let's erase that h, and let's not go quite as far. Let's have h only go to here. Well, now the point's up here. So if I go straight up from there, now I'm here. Now I can look at this secant line, and I can find that slope. It's still not the same as the one for the green one, but it's a little bit closer. So you know what I do? I make h a little bit smaller. So let's erase h altogether. We're going to get h just to be smaller, but what that does, that moves the point here. And now I take that value. Oops. Oh, where'd I go? Well, that's not good. Now I take that value and I look at the slope there. And then I get pointing a little bit closer and I look at that slope. And notice that's getting really close to the slope of the tangent line. And what I do is I'm making that h value smaller and smaller. In fact, what I'm doing is I'm taking the limit as h goes to 0. So the point is right next to this other point. And that slope is almost identical to the slope of the tangent line. So if I look at the limit as h goes to 0 of my difference quotient, so remember that f of x plus h minus f of x all over h, that was the slope of the secant line. But if I look at how those slopes change when I make h smaller and smaller and smaller, closer to 0, I'm getting closer and closer to the actual tangent line slope. If that limit exists, that is what we refer to as the slope of the tangent line. Now, if I look back here, remember, well, we don't have to go there. Let's just flip up a little bit. It's just called differentiation using limits and quotient rules. I don't think it's called quotient rules. I think I misnamed that. I think it's, let's look in the book. Too far. It is called, I'll find it eventually, differentiation using limits of difference quotients. I don't know where quotient rules came in. I'm going to change that to limits of difference quotients. Let's just do that right now. That'll be easy enough. I believe. Can I just go up there? Can I backspace? I can. Difference quotients. And if we spell this correctly, that would be fantastic. Okay, so it's differentiation using limits of, I still didn't spell that right, difference quotients. All right, so there's our title, differentiation using limits of difference quotients. Okay, now we know what we're talking about. So if this limit exists, what we do is we call that, it's not f of x, because it's not the original function, it's the slope. What we call that, we put a little mark right here, we call it f prime of x. This is the definition of what we call the derivative. So this is the derivative of f of x. It's pronounced f prime of x. So when we look at that little mark above it, looks like a quotation mark. I mean an apostrophe. We call that f prime. So f prime of x, that's the derivative. And what it is, it's the slope of the tangent line. It's also, so here we'll put slope of tangent line here so that we have it all together. It's the slope of the tangent line, but more specifically, it's the instantaneous rate of change of the function. Not the average rate of change, instantaneous rate of change of, we'll just say f of x. All right, so that's the derivative. Derivative is going to be the primary thing we do the rest of the semester. Now, we're going to see shortcuts next section, but for now we have to do it using this definition. So we'll talk about it and then we'll see how that lines up nicely for us. Okay, so we've got that. Let me show you a slide that talks about the definition, just so that we see it formally. So let's put that about there. Let me pull this up for you. And notice it's called definition of a derivative. So we'll just copy that, and then we'll go back and paste it in, just so that we can see it and see what we're talking about. Okay. So for a function f given by y equals f of x, its derivative at x is the function f prime, where f prime of x is the limit as h goes to 0, f of x plus h minus f of x all over h. So that's just what we did, provided the limit exists. If that limit doesn't exist, then there's no derivative there. If f prime exists, then we say f is differentiable at x. So we may say find the derivative, or we may say differentiate. That would be the act of finding the derivative. And we'll see that as we do some of these problems. Okay, so that's the definition. What I want to do, let's use this definition to do a couple derivatives. And we're not going to spend a lot of time on it. On the test, I may have you go through the steps to find one like this, but after this section, everything's going to be shortcuts. There's going to be very simple ways to find derivatives. Some more simple than others. Some get a little complicated, but it won't be as complicated as this. So here's what I want to do. I'm going to do a couple problems. Let's start from the book at problem 4. And they ask us a bunch of steps to this. I will show you part of it. I'm not going to show you the whole thing, because they ask you to do something and they ask you to do it 3 times. We're not going to do it 3 times. They give us a function, f of x is negative 2x squared. And here's what they tell us to do. I'll list these over here. They say graph the function. They say tangent line. This is where I'm not going to do all 3, but I'll do 2 of them. Draw tangent lines at x equals negative 2 and x equals 0. They also have x equals positive 1, but those will just run into each other. And then C, find f prime of x. So using that limit of the quotient rule. And then D says find f prime of negative 2 and f prime of 0. And we'll talk about what those mean. All right, so let's go through. So the first thing, let's just draw the graph. We'll just draw it over here to the side. But this graph, negative 2, it's an x squared. The x squared means it's parabola. The negative 2, the negative makes it flip upside down, and the 2 makes it go a little steeper than normal. So the graph's going to look something like this. And we did a negative 3x squared, so it looked very similar to that. But the graph looks something like this. And over here at negative 2, let's see, if I plug in negative 2, that's going to be 4, so negative 8. It's going to be a dot down here, negative 2, negative 8. That doesn't really look much like a negative 8, does it? Kind of ram that into each other. Negative 8. And at 0, we've got just the point 0, 0. All right, so let's go through and see what's happening. So first of all, we need to find this. Oh, draw tangent lines. We better do that. So the tangent line here is going to look something like this. The tangent line here is going to look something like this, right? It's just kind of riding along like a surfboard. Okay, now find the derivative. So now we're at part C. Let's find the derivative. So let's see. So part C, f prime of x is the limit as h goes to 0. F of x plus h minus f of x all over h. All right, we're going to do this. So I've got the limit as h goes to 0. Now f of x plus h, remember that means plug in x plus h here. Minus f of x is just that function itself all over h. Now notice I can't plug in the h equals 0 because now it's undefined. And it being undefined there, I can't do it. So remember that x plus h squared, let's see, aside. Remember x plus h squared is x plus h times x plus h. I'm not going to multiply that out, but remember that was x squared plus 2xh. We did this in the last section, plus h squared. Okay, so I've got limit as h goes to 0, negative 2 times x squared plus 2xh plus h squared plus 2x squared all over h. Let's keep going. So I've got the limit as h goes to 0. Distribute the negative 2 in. I get negative 2x squared minus 4xh minus 2h squared, and then the plus 2x squared from the outside, all over h. Remember, anything that doesn't have an h has to cancel, which they do. I only have 2 terms up top. Both of them have an h, so I'm going to factor that out. I'll factor it out. Well, we'll go down one more line. Limit as h goes to 0. Factor out an h out of the top. I still have negative 4x minus 2h all over h. Now I can cancel the h. Now that there's no h on the bottom, now I can plug in that h equals 0. So notice I'm not going to write limit as h goes to 0 anymore because I'm going to let h go to 0. So that's just negative 4x. That's my derivative. This is f prime of x. This is very exciting. We need to make it look a little bit cleaner. This is f prime of x. Oh, I still don't like it. But now I'm almost happy. There we go. I found the derivative. This is my first derivative. That's a formula for the slope of the tangent line at any point on the curve. So this is a formula for slope of tangent line. Remember when we did that one that was a line itself? There's no x because it didn't change. This one changes depending on what x is. So for instance, if I do part D, which said find f prime of negative 2, oh, I plug it in there. It's negative 4 times negative 2. It's 8. What's this 8? Ah, it's the slope of the curve. This slope right here was 8. When x is negative 2, the slope of the tangent line is 8. In other words, at that point, that instant, when x is negative 2, the graph is going up 8 for each one it goes across. And notice it doesn't go up 8 for the whole one, otherwise it would be a line, which it's not, it's a curve, it changes. But that's instantaneously how fast the curve's changing. And if I do f prime of 0, let's look at that. That was this one here, right? That's the slope of that line. That's a horizontal line. That slope is 0. Well, let's see. So if I plug this in, negative 4 times 0, in fact, is 0. That's the slope of this line. So the slope of the line is going to change depending on what the x is. If you have any sort of curve, if you have just a line, the slope doesn't change. The slope's always the slope. But here the slope of the tangent lines change because the graph is doing different things. So that's the idea there. Hopefully that helps you out. What we're going to do is we're going to look at another one of these to practice just doing some of these. It's problem, I don't know if doing another one of these is really going to help that much. In fact, we'll do number 8, but I'm going to go through the the gist of it a little bit quicker since we've already seen how to do it. But I want you to see how we do that f of x plus ah, f of minus f of x all over h. I want you to see that one more time. So this on problem 8, and this is a much simpler one. This is just 2x plus 3. And from what I said before, notice that's a line. The slope is 2. The tangent line should also be 2. Let's see. So this, again, they want us to do all those steps, but the graph looks like this. We're at 3. We go up 2 and write 1. So the graph looks like this. If I find the derivative f prime of x, oops, I forgot my limit. If I don't do the limit, it's just the slope of the secant line. It's not the slope of the tangent line. All right, so let's see. So I get the limit as h goes to 0. If I plug in x plus h, I get 2 times x plus h plus 3 minus 2x plus 3. Kind of run into that. All over h. Distribute. I get the limit as h goes to 0. 2x plus 2h plus 3 minus 2x minus 3 all over h. Again, we've done one similar to this in the last section. The 2x and the minus 2x cancel. The 3 and the minus 3 cancel. I just have 2x. I just have 2h over h. So what I have, limit as h goes to 0 of 2h over h. Well, now I can cancel out that h. Hey, where'd that go? Now I can cancel out the h. Well, there's no place to plug in the 0 anymore. This is just 2. I want that to be blue. I want that to be black. That's just 2. And what it's saying, since there's no x, it's anywhere that function, the slope of the tangent line is 2. Well, that makes sense. See, if I did this last part, if I did part D, and I did f prime of negative 2, it's still just 2. There's no place to plug in the negative 2. If I plug in f prime of 0, it's still 2. There's no place to plug in the 0. What that tells me is if I go back up to this curve up here, and I go to where x is negative 2, and I do a tangent line right there, the slope of the tangent line is 2. If I go to where x is 0, the tangent line right there, the slope is still 2. So since my function itself is a line, then any tangent line to it is the exact same line. So it will have the exact same slope. And that's one thing we'll look at next time when we see the shortcuts or the rules for derivatives. If your original function, like ours, is just a line, the derivative is just the slope of that line. Notice 2 is the slope of y equals 2x plus 3. The 3 doesn't matter. It could have been 2x plus 9, 2x minus 7. Doesn't matter. It's just the slope. The constant has nothing to do with the slope of the tangent line. So anyway, that was a lot quicker. It was a simpler one, and we pretty much did the whole thing anyway. Okay, so the last thing I actually want to show you is where a function can be differentiable and when it can't. And it's actually a pretty easy concept. So let me pull an example out. And here's our example. And we'll paste this in. Okay. So we paste this in. It's problem 26. The question says, list all points, x values. I think it said x values, not points, where the function is not differentiable. And what not differentiable means, it means there's no derivative. Well, remember the derivative is the slope of the tangent line. So if I go to a point like this right here, and there's an open circle, I can't have a tangent line at that point because the point doesn't exist. The point's up here, but would this be the tangent line? Would that be the tangent line? Would that be the tangent line? I don't know what the tangent line is. So if there's a hole in the curve, there can't be a derivative there because the tangent line has to touch at that point. So anytime it's not continuous, there can't be a derivative there. So the first one we're going to list is we're going to say not differentiable at, well, we'll start with x sub 1. And the reason is not continuous. Let's see, if we go to, oh, that was x sub 0, wasn't it? So not differentiable at x sub 0. Sorry, x sub 1 is this one here. At x sub 1, it actually is differentiable. So we can find the, here I can find the tangent line. It's going to look something like this. Yeah, that one's good. x2, it's not. Think about it. If I'm coming in here, I'm looking at this point. The point exists, so I'm good there. But if I'm coming in from here, the secant line looks like this. If I move it a little closer, the secant line looks like this. If we move it a little closer, the secant line looks like this. But if I come in from the other side, the secant line looks like this. And get a little closer, the secant line looks like this. Those aren't approaching the same number. Coming in from the left, the slope is positive. Coming in from the right, the slope is negative. They don't meet at 0 because it's a corner. There's no nice flat spot for those to get to be 0. If I have something like this, yes, I have a slope of 0 there. If I have something like this, there's no point there. Let's erase that. We'll just draw it as a. So if I have a corner, I'm not approaching the same slope. Off to the left, my slope is this way. Off to the right, my slope is this way. They're not equaling each other. But over here they are. Oh, the slope's here. Now it's a little flatter. 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 It's getting close to 0. Over here, same thing. Oh, it's that, but now it's a little smaller. Now it's a little smaller. Now it's a little smaller. So if it's nice and rounded, the derivative exists. If it's a corner, the derivative does not exist. So let me erase that stuff. That's just a lot of noise going on there. So at x2, it's not differentiable. And the reason is it's a corner. Sometimes they call it a cusp. We're just going to call it a corner. x3, we're okay. At x3, it's nice and rounded at that bottom. What about x4? Nope. We can't do it at x4. Again, it's not continuous. Well, let's do this. We'll say we can't do it at x sub 0 or x sub 4 because it's not continuous. There's a corner at x sub 2, but there's also a corner at x sub 5. So x sub 2 and x sub 5, we have corners. Oh, you know what? That's a corner at x sub 6 because it's a straight line and then it's not straight. So it's coming in towards 0 to the right, but that's never getting close to 0. That's another corner. So it's a corner at x sub 6 also. So at x2, x5, x6, and then there's one other place it's not, and it's right here. The tangent line there is a vertical line, and a vertical line, the slope's undefined. So there is a line, we just can't find the slope. And since the derivative is the slope of the tangent line, we just say, oh, you can't find the slope. So There's no slope at x sub 7 either. And so x sub 7, and the reason that is vertical tangent line. So those are the only three things you need to look at, is if the graph's not continuous at a point, then it can't be differentiable there either. If there's a corner or a cusp, the graph's not differentiable there. Or if there's a vertical tangent line. And on this x sub 8's fine, but there's a lot of points where it's not continuous. Anywhere in between any of those x values, though, it's continuous on all those, it's differentiable at all those points. They just picked some points of interest. But any point along the curve between x sub 0 and x sub 1, it's differentiable at all points in there. So don't think, oh, this curve's only differentiable at what, x sub 1, x sub 3, and x sub 8. Well, the only listed points where it is differentiable is those. It's actually only not differentiable at the points we have listed, 0, 4, 2, 5, 6, and 7. But everything that's not listed, it's differentiable there. All right, well, that is the end of that section. Again, very theoretical today. I apologize for that. This class isn't that theoretical. As we get going, we've done most of the theoretical stuff until we actually get to our last chapter. It's actually chapter 5. No, I believe it's chapter 4, where we look at the other side of calculus, which isn't derivatives, it's integrals, it's anti-derivatives. It's going backwards from this. But all of chapters 1, 2, and 3, and what we're going to touch on 6, all have to do with the derivative. So we're going to be derivatives most of from now on. After these first 4 sections, we get out of the theoretical realm and we go into more practical applications of these. Okay, so anyway, do this, work on the homework, and I will talk to you in our next live session. But hang in there. I think the more this you do, the more you'll see it makes sense, and hopefully you'll be able to follow along real well. Get the homework done so that on the test you can excel and do real well. All right, that's it. I wish you all the best, and I will see you all very soon.